I see a multiple choice question about RidgeClassifierCV, a machine learning algorithm, and how it handles multicollinearity, which is when predictor variables are highly correlated. The question tests whether you understand how RidgeClassifierCV works in this specific situation. Let's break it down. This statement suggests that RidgeClassifierCV will struggle with multicollinearity. However, RidgeClassifierCV is specifically designed to handle multicollinearity better than ordinary least squares regression, so I'd consider this statement potentially false. Here, we're discussing the alpha's parameter in RidgeClassifierCV. It determines the strength of regularization. While it helps, RidgeClassifierCV doesn't magically eliminate multicollinearity's effects. The statement is partially true, but it needs more nuance. This statement hits the nail on the head. RidgeClassifierCV uses cross-validation to find the best alpha, improving its performance, especially when dealing with multicollinearity, which is why it is more robust than ordinary least squares. This is also correct. The regularization in RidgeClassifierCV shrinks coefficients, reducing their sensitivity to multicollinearity compared to standard logistic regression, which does not have this built-in regularization. This is the title summarizing the focus of the problem. It's highlighting the central concept that I'll need to understand: the relationship between RidgeClassifierCV and multicollinearity. I think statement A is incorrect. Ridge regression, the method behind RidgeClassifierCV, is specifically designed to handle multicollinearity, which is the problem of having highly correlated features in your dataset. So, it's unlikely that it will perform poorly just because of multicollinearity. Statement B is partially true. The alpha's parameter, which controls the strength of regularization in ridge regression, is automatically selected by RidgeClassifierCV using cross-validation. However, this doesn't completely eliminate the effects of multicollinearity, but instead it minimizes its impact. This statement is correct. Cross-validation is a great technique. It helps RidgeClassifierCV find the best alpha value, leading to a more reliable model that is less affected by multicollinearity. It's like trying out different model settings on different parts of the data, and choosing the one that works best overall. Statement D is correct. Ridge regression shrinks the coefficients, the numbers that tell you how much each feature affects the outcome. This shrinkage makes the coefficients less sensitive to the instability caused by multicollinearity, compared to simpler methods like standard logistic regression. This phrase sets the stage. We'll explore how RidgeClassifierCV, a type of classifier using ridge regression, handles datasets with multicollinearity, high correlation between features. I'll explain what that means and why it's important. The question introduces a scenario. You're using a specific machine learning algorithm, Sklearn, linear_model, RidgeClassifierCV, to classify data with a problem, multicollinearity. I will guide you through assessing the algorithm's behavior in this situation. This statement is correct. I love cross-validation. It's a powerful technique to find the best model settings by testing on different subsets of the data. This makes RidgeClassifierCV more reliable because it accounts for variations in the data. The alpha, a regularization parameter, helps prevent overfitting. Also correct. RidgeClassifierCV uses regularization, which basically shrinks the coefficients. Think of it as reducing the impact of noisy or strongly correlated features, leading to more stable coefficients, the numbers that determine the model's predictions. This is unlike standard logistic regression, which is more susceptible to unstable coefficients with multicollinearity. Partially correct. While RidgeClassifierCV does automatically pick the best alpha value through cross-validation, again, that's awesome. It doesn't completely solve multicollinearity. It significantly reduces its impact but doesn't eliminate it entirely. This is the final outcome after RidgeClassifierCV processes the data, accounting for multicollinearity and using cross-validation and regularization. The output would be the classification results, for example, which class each data point belongs to. The dataset used as input to RidgeClassifierCV. The critical part is that it contains multicollinearity. This means that some of the features, the columns of data used for prediction, are highly correlated with each other. A statistical method to evaluate model performance. The data is split into subsets. The model is trained on some subsets and tested on the others. This helps prevent overfitting and provides a more realistic estimate of how the model will perform on new, unseen data. A technique to prevent overfitting by adding a penalty to the model's complexity. Ridge regression, specifically, adds a penalty proportional to the square of the magnitude of the coefficients. This encourages smaller coefficients, which makes the model less sensitive to multicollinearity. Incorrect. RidgeClassifierCV is specifically designed to mitigate the effects of multicollinearity, so it's unlikely to perform poorly solely because of it. I'm focusing on how RidgeClassifierCV, a type of linear model, deals with multicollinearity. Multicollinearity means that some features in your data are highly correlated. This can cause problems, because it makes it hard to figure out which features are truly important for prediction. Think of it like trying to figure out the effect of sunshine and warmth on ice cream sales. They're related, making it hard to isolate each effect. RidgeClassifierCV is specifically designed to tackle this challenge. I'll explain this. RidgeClassifierCV uses regularization. This means it adds a penalty to the model's complexity, specifically penalizing large coefficients. This penalty makes the coefficients less sensitive to those pesky correlations between features, unlike plain logistic regression. The effect is that the model's results are more stable and reliable. It's like adding a stabilizer to a wobbly table. The table still works, but it's much steadier. I'm explaining why cross-validation is crucial here. Cross-validation helps us find the best model by testing it on many different subsets of the data. This makes the model less likely to overfit to the training data and more robust to things like multicollinearity. It's like trying out a recipe on several different ovens. If it works well across all ovens, you know it's a good recipe, even if some ovens are a bit quirky. Let's talk about the alphas parameter in RidgeClassifierCV. This parameter controls the strength of regularization. RidgeClassifierCV cleverly uses cross-validation to find the best alpha value, making the model better at handling multicollinearity. It's like automatically adjusting the stabilizer on that wobbly table to find the perfect balance. The quiz question asks us to think about how RidgeClassifierCV, from the Sklearn library, behaves when we have multicollinearity in the data. We are given options about its performance, and our job is to choose the right ones. This section introduces the core topic: how RidgeClassifierCV, a type of linear model from the Sklearn library, behaves when your data has multicollinearity, that is, when some of your predictor variables are highly correlated. We'll explore whether this affects the model's performance. The question tests my understanding of how RidgeClassifierCV handles the problem of multicollinearity. It's a multiple-choice question where I have to evaluate several statements about the algorithm's behavior in this specific context. Let's get to the statements. I am given a scenario. I'm using a specific machine learning algorithm, RidgeClassifierCV, from the Sklearn library, on a dataset where features are strongly correlated. The goal is to determine which statements accurately describe RidgeClassifierCV's behavior in this situation. This statement suggests RidgeClassifierCV will fail because of multicollinearity. I need to check if this is true or false based on how RidgeClassifierCV works. This statement focuses on the ALPHAS parameter of RidgeClassifierCV, which is related to regularization. I will consider if the automatic alpha selection completely solves the multicollinearity problem or only mitigates it. Here, we are discussing the use of cross-validation in RidgeClassifierCV. I need to determine if this method makes the algorithm more resilient to multicollinearity problems compared to a standard least squares approach. This statement compares the coefficient sensitivity of RidgeClassifierCV to that of a standard logistic regression model when multicollinearity is present. I must determine if the regularization in RidgeClassifierCV leads to less sensitivity. I'm examining how RidgeClassifierCV, a type of linear model from Sklearn, handles multicollinearity. When features in your dataset are highly correlated, this is important because multicollinearity can make it hard to accurately estimate the influence of each feature. I will analyze how RidgeClassifierCV addresses this issue. We're using RidgeClassifierCV to classify data with significant multicollinearity among the features. I need to determine which statements accurately describe its behavior under these circumstances. I'm investigating the effect of multicollinearity on the performance of RidgeClassifierCV, specifically from the Sklearn library in Python. I'm looking at this model's strengths in handling this specific challenge in machine learning. This statement suggests that RidgeClassifierCV might not work well with multicollinearity. However, I know that's not entirely true because ridge regression is designed to handle it, but it's a point I need to consider carefully. This statement talks about the alphas parameter. Alphas are different values of the regularization strength, which helps prevent overfitting by controlling how much the model considers the coefficients. RidgeClassifierCV uses cross-validation to find the best alpha value, improving its ability to handle multicollinearity. I need to assess how accurate this statement is. This statement correctly points out that RidgeClassifierCV uses cross-validation to find the best regularization parameter. Cross-validation helps prevent overfitting and makes the model more robust to issues like multicollinearity. I'm analyzing this statement to see if it's fully true. This statement claims that RidgeClassifierCV coefficients are less affected by multicollinearity than those from a standard logistic regression model. This is due to regularization, and it's a key advantage. I will examine whether this is true. Multicollinearity means that predictor variables, features, in my dataset are highly correlated. This can make it tricky to determine each feature's individual effect because they're so intertwined. Regularization is a technique I use to prevent overfitting. It reduces the model's complexity, making it less likely to capture noise in the training data. Ridge regression, which RidgeClassifierCV uses, adds a penalty to the model based on the size of its coefficients, thus shrinking them. Alpha controls the strength of regularization. A larger alpha leads to stronger regularization, meaning that the model's coefficients are shrunk more towards zero. This helps to reduce overfitting and improve the model's ability to generalize to unseen data. Cross-validation is a crucial technique I employ to evaluate a model's performance. It involves splitting the data into multiple subsets, folds. I train the model on some folds and test it on the remaining fold. I repeat this process for all folds and average the results to get a more reliable estimate of the model's performance on unseen data. This helps me avoid overfitting and select the optimal alpha value. I see that this title introduces the core topic: how the RidgeClassifierCV algorithm, a type of linear model in machine learning, handles multicollinearity. Multicollinearity is when multiple predictor variables in your data are highly correlated, which can make it difficult for a model to understand their individual effects. The goal of this problem is to determine how RidgeClassifierCV addresses this challenge. This question sets up the scenario. You're using a specific machine learning algorithm, RidgeClassifierCV, from the Sklearn library, and your data has a problem: high multicollinearity. You need to figure out which statements correctly describe how RidgeClassifierCV will behave in this situation. This statement focuses on the ALPHAS parameter of RidgeClassifierCV. ALPHAS controls the strength of regularization. Regularization is a technique to make the model less sensitive to noisy data and prevents overfitting, a situation where the model becomes too closely tied to the training data and doesn't generalize well to new, unseen data. I'd say that while the automatic alpha selection helps, it doesn't completely solve multicollinearity, it just minimizes its effects. This statement points out the crucial role of cross-validation. Cross-validation is a resampling technique that helps assess the performance of a model by training it on parts of your data and testing it on the remaining parts. This helps avoid overfitting and builds a more robust model, particularly useful when multicollinearity makes estimates unstable. The comparison to ordinary least squares, OLS, highlights that RidgeClassifierCV, with cross-validation, is a superior approach in this case. This statement directly addresses the impact of multicollinearity on model coefficients, the numbers that determine the influence of each predictor variable. It claims that RidgeClassifierCV coefficients are less affected by multicollinearity than those from a standard logistic regression model, which doesn't use regularization. This is true because regularization in RidgeClassifierCV shrinks the coefficient values, reducing their sensitivity to the instability introduced by multicollinearity. This option suggests that RidgeClassifierCV will do poorly because of multicollinearity. However, that is incorrect because RidgeClassifierCV is specifically designed to handle multicollinearity more effectively than standard linear models due to its use of regularization and cross-validation. This simply indicates that the preceding options are the possible answers to the main question. It doesn't require further explanation.